Ever stop to think about what's happening? Like
Yeah.
deep down inside your phone or computer, all those clicks, commands, every single thing a device does, it all ultimately boils down to super simple decisions, right? Billions of them a second, just yes or no, on or off.
Mm.
Today, we're doing a deep dive into exactly that, the absolute bedrock of digital tech, logic gates, and Boolean algebra. We've been digging through a bunch of sources that really break these concepts down, how the individual pieces work and then how they snap together to make the complex systems we use every day.
Yeah, and our mission really is to give you a clear handle on these core ideas, not just what they are, but really why they're so crucial, how they, lay the groundwork for everything digital. You should have a few aha moments today, I think, about the logic humming away inside your gadgets.
Okay, so let's unpack the basic building blocks then. The logic gates. Our sources point to a few essential ones. Think of them like the absolute fundamentals. You've got the inverter or NOT gate. Simple job, clips the signal. Then there's AND or R and the exclusive or XOR.
All right, those are the main ones.
But the cool part, I think, is how you combine them. Like, stick an inverter onto an AND gate and boom, you get a NAND gate.
Exactly. It's modular. These simple things combine to create much more complex functions. That's the whole basis of digital design, really.
So how do we keep track of what they actually do?
Well, that's where the truth table comes in. It's an absolute fundamental tool. Basically, it's just a list. It shows every possible input combination.
Yeah.
A is 0, B is 1, that sort of thing, and tells you exactly what the output will be for each case. Super clear.
Right.
And the powerful thing is, if you have two circuits, maybe they'll look totally different. But if their truth tables are identical,
They do the same job.
functionally equivalent,
Yep.
exactly. It's like the ultimate definition of what the circuit achieves.
And it's interesting how our sources show this works for, say, an OR gate. You can draw its symbol, right?
Yeah, schematic.
Or write out its truth table, or express it with that Boolean algebra notation, or even see it on a timing diagram.
Or in code, like Python.
Yeah. It shows how, universal these ideas are across different fields.
Definitely.
Okay, let's zoom in on two really key ones, or R and AND. The OR gate. Well, it's kind of intuitive, isn't it?
I think so.
Output is 1 if any input is 1. It only outputs 0 if all inputs are 0.
That's right.
And the expression is x equals a plus b. Read A or B.
Simple enough.
So here's a quick check for you listening. What's the only way to get a low W output, a 0 from any OR gate? Just think about it for a sec.
Yeah.
As the sources confirm, it's when all the inputs are low W.
That's the only condition.
Okay, switching gears to the A and D gate, this one acts more like a multiplication, right, with zeros and ones.
That's a great way to think about it.
The output is 1 only if all the inputs are 1, any 0 input, and the output is 0.
Right.
And the expression is x equals a dot b, A and D B. Okay, another quick one for you. Imagine a 5-input AND gate. What's the only way to get a high GH output? A 1. You probably got all 5 inputs have to be 1.
Except,
Now, here's a fun true or false from the sources. An AND gate output will always differ from an OR gate output. True or false? What do you think? It's actually false, which is kind of surprising. Sometimes their outputs can be the same. Depends on the inputs.
yeah, they aren't always opposites, even though their core logic feels different. And speaking of simple gates, we shouldn't forget the not-E gate, the inverter.
Right, the flipper.
Exactly. Seems basic, just flips a 0 to a 1 or a 1 to a 0, but it's absolutely essential for negation. And it's worth noting there's a slight difference sometimes in how it's used. You might see not A for a single true-false thing.
Okay.
But then there's a bitwise not, often written with a tilde, like A.
Yeah.
That applies to multiple bits.
So like a whole number represented in binary.
Precisely. If A is, say, binary 0, 1 to a 1, then A becomes 10, 10. It flips every single bit in the number, not just one logical value.
I see. So it's more granular.
Exactly.
Yeah.
Just shows its use beyond simple logic, too.
So, okay, we have these gates, we have truth tables, but trying to design something complex, like you said, a processor, using just diagrams or massive tables.
Yeah.
That sounds like a nightmare.
Oh, it would be completely impractical. Way too cumbersome.
So there must be a better way, a more elegant language for this.
Absolutely. And that's Boolean algebra. It gives us these algebraic expressions.
The ones with the dots and plus signs.
Exactly. A dot for A and D, a plus for OR, and usually a bar over a variable or maybe a slash or apostrophe for not inversion.
Okay.
But the key thing, just like in regular math, is the order of operations. There are rules you have to follow. Precedence rules.
Ah, okay. Like PEMDAS, but for logic.
Sort of, yeah. First, you do any inversions of single variables.
Got it. Not sets first.
Then, anything inside parentheses, standard stuff.
Right.
Then you perform all the AND operations before you do any OR operations. Unless, of course, parentheses change that order.
Okay, Andy before or.
And finally, if you have a bar over a whole chunk of the expression, like a group inversion, you have to figure out the value inside that expression first, following all the other rules, and then you invert the final result.
Okay, that makes sense. Work from the inside out for those big inversion bars.
Precisely.
Our sources showed this with a NOR gate, right?
Yep.
Which is just an OR gate with its output immediately inverted.
Yep, an OR followed by a not T.
And often in diagrams, you don't even see the full inverter symbol, just a little circle on the output of the OR gate.
That little bubble, yeah. It's shorthand for inversion. Save space.
And knowing those precedence rules lets you trace the signals, put in zeros and ones at the start, and figure out the final output step by step.
It does. And the real beauty here, just like with regular algebra, is that you can manipulate these Boolean expressions. You can simplify them.
Simplify? How?
Well, Boolean algebra follows laws similar to normal algebra. The commutative law AORB is the same as BORA.
Order doesn't matter.
Right. The associative law, how you group things with the same operator, doesn't matter. AOR, BORC, is the same as AORB, ORC. And the distributive law, you can distribute AD over OR, or OR over A and D, similar to multiplying into parentheses.
Ah, okay. So you can rearrange things.
Exactly. And there are specific simplification rules, too. Some are obvious, like A and D, A is just A.
Makes sense.
Others are less intuitive, maybe need a bit of memorizing, but they let you take a complex expression and boil it down, potentially using fewer gates, which means a cheaper, faster circuit.
So this algebra isn't just descriptive, it's a tool for optimization.
Absolutely critical for that.
Okay, this feels like it's getting really powerful now. How do these rules and ways of writing things really unlock the potential? What makes it jump from theory to, building computers?
Well, a huge piece of that puzzle is De Morgan's theorems. They are incredibly important.
De Morgan's. Okay, what do they do?
They basically give you a way to swap A and Ds and ORs when you're dealing with inversions.
Swap them.
Yeah. So if you have an inverted OR operation, like not A OR B, De Morgan says that's identical to not A and D, not B.
Huh. So the OR becomes an A and D, and the inversion moves to the inputs.
Exactly. And it works the other way, too. Not A and D B
Mm-hmm.
is the same as not A or not B.
Okay, wow. Why is that so useful?
Because it gives you flexibility.
Yeah.
It often lets you simplify expressions dramatically or change the type of gates you need to use, which can be really handy in design.
And that flexibility, that connection between NADs and ORs through inversion, that leads somewhere really big, doesn't it? Something about universality.
It does. That's the payoff. It
Sure.
leads directly to the concept of universal gates. The NAND gate is the classic example, but NOR works too.
Universal how?
Okay, get this. If you have just a simple two-input NAND gate, you can actually build all three basic logic functions using only NAND gates.
Wait, seriously? Just NAND?
Just NANDs. You can wire up NAND gates to act like a NOT gate.
Right?
You can wire them up to act like an AND gate.
Right.
And using De Morgan's theorems implicitly, you can wire them up to act like an OR gate.
Wow.
So think about what that means if you can make NOT, AND, D, and OR using only NAND gates.
You can build anything, any logic circuit, any Boolean expression.
Exactly. That's the aha moment. Give me a big enough pile of NAND gates, theoretically. I could build a Pentium processor.
Just from that one simple gate repeated over and over.
That's the power of universality. It's incredible when you think about it. One simple building block is all you actually need.
That is pretty mind-blowing. Okay, so stepping back a bit. Beyond the ones and O's, the algebra, is there a more, intuitive way to think about what these gates are doing functionally, what their job is?
Yeah, that's a good question. You can definitely think about them in terms of their function. Take the AND gate.
Okay.
You can think of it as an enable or disable function, sometimes called a gating function. Imagine one input, B, is like a control signal.
Right.
If B is 1, it opens the gate and lets the other input, A, pass through to the output. The output just follows A.
Okay.
But if B is 0, it closes the gate. It blocks A, and the output stays at 0 no matter what A does.
Ah, like a digital switch controlled by B?
Exactly. Controlling the flow of information.
What about OR?
The OR gate. You can see that as more of a merging function. It takes any high signal, any one, from either input A or input B, and combines them or merges them into a high output.
Like saying, if this OR that happens, signal the result.
Pretty much. And then XOR, the exclusive OR. That one's interesting.
Yeah.
It could be seen as a selectable inverter.
Selectable inverter.
Yeah. If one input, say B, is 0, then the other input, A, just passes straight through to the output. Output equals A.
Okay.
But if B is 1, then A gets inverted at the output. Output equals not A. So B acts like a switch that decides whether to invert A or not.
Huh. That's quite versatile.
Very. It's also used as a basic comparator. The XOR output is 0 only when the two inputs are identical. If they're different, the output is 1.
So it can check if two bits are the same or different?
Yep. Useful in many circuits.
So when you put it all together, I mean, this isn't just abstract stuff for engineers, is it?
No.
This is literally the language everything digital speaks.
It really is. Underneath all the apps and interfaces, it's these fundamental logic operations, these simple on-off decisions, driving absolutely everything.
It's kind of staggering.
It is. From the simplest calculator chip to, massive AI models running in the cloud, it all traces back to this.
So we've covered a lot today. We started with those basic gates, A and D, I are not, and their truth tables.
Mm-hmm. The foundations?
Then we jumped into the language of Boolean algebra, the dots and pluses, the precedence rules.
And how that algebra helps simplify things.
Right, especially with De Morgan's theorems, which felt like a real key.
Definitely unlocks a lot.
And that led us to the amazing idea of universal gates, like NAND, how you can build literally anything from just one type of gate.
The ultimate building block.
We've really seen how these tiny logical choices enabling a signal, merging data, flipping a bit, form the absolute bedrock of, well, everything.
Yeah, understanding these fundamentals, even just conceptually, really gives you an appreciation for the incredible complexity built on top of such elegant simplicity. It's the hidden architecture of our digital lives.
So here's something to chew on. The next time you're using your phone, your computer, whatever, just pause for a second. Try to imagine that invisible whirlwind happening inside billions of these tiny logic gates, flipping, gating, merging signals, enabling everything from displaying this text to processing your thoughts into a search query. It all starts here. Makes you wonder, what other simple, fundamental ideas might hold that kind of universe-building power, hiding just beneath the surface?